With that, I'm going to talk to you about a revolutionary transformational sensor of the future, the technology called SansEC. Resonance and inductive technology isn't anything new. It's been around a long time. Michael Faraday, several, at least a couple of 200 years ago, invented the inductor, the Faraday cage, motors, technologies that relied on coils and spirals and electromagnetism to perform their functions. And also Tesla, which we know, the polyphase AC motors, everybody knows Tesla coils and such. These technologies that started in this rudimentary level of development are in everything. All of our technologies today. They're in motors, they're in our cell phones, they're in our communication systems, they're everywhere. SansEC, I believe, has the potential to be a technology that becomes ubiquitous as well, that shows up in many things. And we stand on the shoulders of these giants that are the fathers of resonant technology, but they did not use them as sensors, they used them as devices. Another gentleman that you've heard, Dr. Stanley Woodard, who's a friend of all of us and the inventor of the SansEC technology. It's an incredible concept that he was able to see about 10 years ago, a little more than 10 years ago. And he pushed this technology, this vision forward to the point where we have it today. There's a number of patents and papers and insights that Stan developed that we're still working on today. Our technology team has developed, has added to that with a few patents and things that you will see today. But the core of the idea, the inventor of the concept, was Dr. Stan Woodard, and we very much miss him. He recruited Dr. Wong, to the effort, and we're carrying forth that legacy of Dr. Woodard. I am simply a voice. I'm simply a disciple of his message. Stan was not just an incredible engineer and scientist, but he used the other part of his brain, the right part of his brain, for creativity and such. And he was inspired by many things. Spirals are all around us. Why? Why are they there? We see them in the shapes of our galaxies. We see them in the shapes of biological animals, like the nautilus shell there. They show up in our storm systems, hurricanes. There's a coordinate in the Mandelbrot set, fractal geometry, where these spirals show up. They show up in biology. There's a picture missing here. Like I said, we take our image clearances seriously, and I don't have the proper images for there, but you can use your favorite browser system and search on biotendrils, and you'll see some amazing spiral plants and succulent spirals, that cactus-like plants that have these amazing spiral structures in them. Why are they there? Why are they there? They show up in our physiology. All of our fingers have these fingerprints and ridges and whorls, and a number of them are spiral shaped. Why are they there? I actually have a hint on that one, and we'll talk about it a little bit later, because it actually may have some relation to SansEC. There's spirals in physiology inside of our ear. The anatomy of the human ear has a cochlea with the spiral there. Keith just mentioned the sensing technologies for biological senses: taste, smell, touch, vision. Can SansEC be adapted to this? There's some hints that it actually can. They show up in art. Stan was big at towards the end of his life there. He was taking SansECs and making art objects out of them, and we test them for the resonance characteristics just for the fun of it. And they do. They just work. They show up in architecture. Again, a couple of images that are missing there, but if you Google those or use your favorite browser to take a look at the Great Alderstone Ugaba. It's an ancient structure that has spirals in it. The tops of classic Greek columns, Roman columns, have these spirals in it. Ancient Neolithic cave carvings have these spirals in it. Why does it capture the human mind so much? The spirals in mathematics, Archimedean, logarithmic spirals, Fibonacci. There's a number of mathematics spirals that come into play. So spirals in SansEC sensors. What is SansEC? SansEC is a term that Dr. Woodard coined, meaning sans without EC electrical connection. It is a spiral resonance sensor that, without any direct electrical connection to the entity, the phenomena, the physical phenomena that it's sensing, can sense that environment, and then with the antenna can be remotely interrogated such that information about the environment, whether it's electrical, mechanical, chemical, acoustic, many different physical phenomena can be sensed by the sensor. We're going to see how all that works here today. You can kind of think of it, think of a SansEC as a kind of like a bell. And a bell, and it's a certain physical size and geometry, and because of that physical size and geometry, it has certain unique characteristics to it, a frequency that it will resonate at. You're going to hear that word resonance a lot. We all learn about resonance in school. I talked with Dr. Goodman of DARPA, and he says that's one thing that we're all really kind of undereducated in our formal educations. And resonance is a big phenomenon. It shows up in all kinds of things, mechanical systems, electrical systems, and it's a big phenomenon. And this resonance phenomena, when you strike a bell, it will resonate at a particular frequency. And so a SansEC is similar to that. The striking hammer that we use is electromagnetic energy that we send to the sensor. It strikes it and rings it at a self-resonant frequency that's particular to the geometry of the spiral itself, and then returns that back, and we measure that as a signal. And that signal comes in the form of amplitude, a frequency. If we have a vector instrument instead of a scalar instrument, we can see that in the terms of phase, and also we can infer bandwidth. And from those quantities or characteristics, we can infer intelligence about the environment that the sensor is in. And so just like a bell, if you were to immerse a bell with water and strike it, you get a frequency shift, the sound changes. SansEC is it's a good metaphor for how SansEC works. The brilliant thing about Dr. Woodard's invention of this technology is that no one else would have seen it. I work in electromagnetics, and to electrical engineers, it's an open circuit device. To electrical engineers, an open circuit is something it's a device that's broken. Or if it's not broken, it has a switch in it, and the switch is open, so it's turned off. But Stan was able to see past that, and he experiments and studies on this and saw that this was a very useful phenomenon that could be exploited. And this open circuit is the key part of SansEC technology. And then the other part is it's completely wireless. It doesn't have to be in direct contact with its interrogation device. So those are the two key points of it. It's open circuit, that's what makes it, that's one of the unique features of it. And it doesn't have to be in direct contact with the interrogation system. In that, it can measure temperature, chemical, water content, liquid level, a number of applications that you're going to see. My boss, we all have a lot of bosses, George Shikuski, comes up and talks a little bit about how we got involved into SansEC with Dr. Woodard, and a number of applications later in the day. So, because it's an open circuit sensor system, and it is an electrical system, we can create what's called an equivalent circuit model, and we can gain some deeper understanding as to how SansEC works and what it is. If you look here, we have a signal source represented by a resonant structure of RLC components. That's the antenna that strikes the SansEC. It sends out the energy to energize it and to create its self-resonance. And in the middle, we have the sensor itself, and there is mutual coupling between the inductive components, the magnetic components of the antenna, and the magnetic components, the inductive components of the sensor itself. And then on the end there is, in material science, particularly in electrical materials science, we like to call it a material under test, the environment that the SansEC is in contact with. And it also has an LRC component to it. So when we break this down into an equivalent electric circuit model, we can get greater insights into the physics and functioning of a sensor, and we can move from there then to equations and get the deep science insight as to what a SansEC sensor is doing. First of all, you see this spiral here with a current distribution imposed upon it from the interrogation antenna, and that shows up as a cosine distribution. If we were to stretch this structure out into a wire, you see that at one end of the wire it is fenced in. It's blue, which indicates that there's low current or no current on the ends, and also at the other end there's no current. That's a condition that's forced by the physics of electric energy impinging onto a wire structure. So what we see here is the fundamental mode of current distribution onto the SansEC sensor. It's governed by this equation here. The charge distribution would be assigned to be the exact opposite of that. So that's when we're going to charge that. This is the only equation that's charted in the presentation, but it's important. This one's going to point out why SansECs work. All materials in the universe, including the vacuum of space, has intrinsic material properties associated with it. They're known electrically as permittivity, electrical permittivity, and electrical permeability. Electrical permittivity is the ability of a material to store an electric charge. The electrical permeability of a material is its ability to store a magnetic charge. All materials in the universe have this, and the SansEC exploits that. The magnetic property is given by the mu, quantity u sub 0, and u sub r, the relative value, and we find that in the inductive structure, the spiral itself, which creates the inductance, gives us this equation here, and this is part defines the geometry, spatial components, but this is the key part here, is the magnetic, how the sensor interacts with the magnetic properties of a material. The SansEC between the traces, any parallel conductors creates a capacitance, works on the electrical permittivity, shown by these two terms here. And so any change in a material's electric permittivity or electric permeability will affect the resonance frequency of that sensor. So all materials exhibit this. And if I heat up a material, its dielectric property, we call these dielectric qualities. These dielectric properties will change. If I bend a material or stress a material, the dielectric properties change. If I want to sense something such as a gas, I can take a material that's affine to that particular chemical species, place that material onto the SansEC, and if the gas, say hydrogen, attaches to that affine material, it will change the material's dielectric properties, and SansEC will sense them. It's an incredible phenomenon, really incredible. It means SansEC can sense anything. Okay, in this chart here, we see the sensor in free space given by the green curve there. And then a dielectric substrate is placed on the material, on the SansEC. Some material is placed there, and we sense it, and we get a very distinct resonance shift. So that's the these equations can get more complicated. Some extra terms can be added to it, but in a nutshell, that's what we're working on. That's how the sensor works. In the first chart, in the chart just before this, you saw the current distribution on the sensor, and that was for what we call the fundamental mode. But you can have higher order modes, harmonics. So these resonant modes that can be impinged upon the SansEC sensor, and it goes into its self-resonance phenomena to create the fundamental frequency response and then harmonics of that response, can show up like this. And in this color diagram, you can see if we wrap that into a spiral, you would get some pretty complex looking color structures there. That can be exploited in the sensor. In the fundamental mode, your strongest fields would be somewhere in between the center portion of the SansEC. But if you go and start operating on a harmonic, then you get increased, essentially increased resolution. Dr. Wong coined the term kind of like a microwave microscope. It's kind of like that. By shifting to the mode, shifting to different modes, we shift where the SansEC is sensing on the material that it is in contact with. And that can be exploited. These are some computational models that show the interaction of SansEC with materials. Here's a cutaway of a SansEC on a dielectric substrate. There is a void established underneath the SansEC in the substrate structure. And in this case, you get the electric field distribution, and we've turned off the void, and so there's no damage there. And that's the electric field distribution you would see with an interrogation antenna here, a SansEC on the surface, and the interactions of the electric field with the material under test. In the situation where there's a void, you can see strong electromagnetic fields coupling into that void. The void is either vacuum or free space, and it has a different dielectric property, a different mu, different epsilon, different permittivity, a different permeability, a different permittivity. And that change is realized in a frequency shift. The lower curve there with no inner damage. I think this is just a couple of millimeters of a gap or damage in the structure, and we get a frequency shift example of that. The SansEC is a very resilient sensor. This is another amazing property. I'm going to back up a little bit. When I first saw Dr. Woodard demonstrate his technology in, I think it was like year 2000, early 2000s. It was at a technology fair, a little small thing that we had at Langley Research Center. And I came by and I saw it, and I was like, okay, yeah, I didn't get it. I didn't get all of these things here. And it takes a little bit of time to get it. I've been in this business for a long time in electromagnetics, and I could not grasp the concept of this open circuit device. It wasn't until George Shukovsky, a little bit later, met with Dr. Woodard in, I think it was the year 2009, and started a collaboration with him. And George came over and said, hey, Ken, come back, let's talk about this. And Dr. Wong and Dr. Woodard took me to their lab. I spent an entire day with them. We had lunch and dinner. And they showed me some things that just blew my mind. And I finally got it. I said, wow, this is an incredible sensor. And at that moment, I told Sam, I am your disciple. This is an incredible technology. So here's one of the other incredible things about it. It is a super resilient sensor. If the sensor takes damage, it still resonates. Here's a simulation of the damage. In the lab, we'll do some tests when we come over for the tour. But here's a simulation of the sensor that's undamaged. You see the current distribution. We take a chunk out of the corner of the material. Those lines all go to blue, but the continuous other loops begin to resonate. They just resonate at a different frequency. So if you can make use of that in some product designs where you may want to sense damage through a material or such. Or if you don't want to take damage, but you want your sensor to still be sensing and it does happen to take damage, you just recalibrate. You reestablish a baseline at the new resonance frequency, and it continues to go on and sense. It's an incredible property of the sensor. Okay, we're going to move on to what does it take to do the measurements, the things that you would need to do, or in collaboration with us that we could help you with, to actually conduct SansEC measurements and sensor development. We have a facility in the electromagnetics and sensors branch that is the HERF lab, the high intensity radiated fields lab. You'll see that later today. Some amazing technology has taken place in that lab. And we have adapted a portion of it for our SansEC work. And in that laboratory, we have a number of different instrumentation techniques. This is a system that Dr. Wong and Dr. Woodard developed here, the magnetic field response measurement acquisition system. There's a handheld unit that they developed. You'll see that today, too. From my background with network analyzers, we deploy those to make SansEC measurements. They're vector instruments instead of scalar instruments, so you can get that magnitude and phase quantity. And here we have I have to make a disclaimer here that NASA does not endorse any products. You'll see some trade names in this presentation, and NASA does not endorse any of the products. But they're presented here for you to just get an idea. There are other manufacturers, and they make just as well instruments. But this Agilent performance network analyzers, one such instrument that we can use to generate the RF energy that interrogates the sensor, that pings the sensor and creates its self-resonance response. Here's another one. You see that in the lab. And there's a smaller portable one that you'll see in the lab. But the point that I want to get here is our team, Trot Hong and I, just recently, within the past couple of months or so, discovered a chip. That's not a missing picture there. That is actually a little microchip. It costs $8. This is a $250,000 instrument. This is about $100,000 instrument. This is about 30,000. That is $8, and it can do a number of functions. It's a network analyzer that this is. We're going to work really hard over the next period of time that we have on the project to implement that system. If we can implement that system into a SansEC sensor, reduce the size, as Dr. Belton was talking earlier, we can reduce the size, we can make these sensors cheap and ubiquitous. They will be everywhere. Turn them over to you. We want you to continue to start developing these things yourselves right now. But we'll turn these things over to you, and they will show up everywhere. The ideas that you will have to how to implement them will show up everywhere. This is a schematic of the insides of that chip. It's very similar to the schematics of $300,000, $250,000 network analyzer. $8 in bulk. Actually, I think it was $7 in bulk, $8 the other way. These are some other instruments in the lab. We have spectrum analyzers. They have good receivers as well. You can see a number of those today. And then interrogation antennas. The interrogation antenna is nothing complicated. It's just a magnetic loop antenna. Here's a commercial magnetic loop. They've got a little special feature in them. But you can just take a wire, bend it into a loop, and you've got your interrogation antenna. It can be anything, any conductive material to make this antenna out. Here's a couple over here. These are near field systems for interrogating the sensor up close. We thought it would be a challenge. It was a challenge to increase that distance to beyond the near field using higher gain antennas and directional antennas, such as the far field horn or log periodic. There's other Yagis, lots of different types of antennas that can be used to direct energy in the lab. We've done a demonstration with very low power from 30 feet away. We think that you can interrogate Larry Tycatch has a concept application that you'll see later. And we think that you can interrogate antenna SansECs from very long distance. Building rapid prototyping SansEC sensors, we use an instrument, a device called a click and cut. There's two of them there. We're starting to look into 3D printers to 3D print SansEC sensors. I'm going to talk about moving into other dimensions. I had a talk with one of our attendees in the audience today. Had a concept of 3D. It's like, wow, that's pretty cool. You guys, when you start on this, the ideas are just going to come. The applications are they're just going to spew forward. Materials that you can use for making SansEC sensors or the antennas that need to be conductive materials. This is a chart I put together a number of years ago showing all the materials that are in the little blue boxes that are available to you. You know, the familiar ones of copper, silver, gold, if you want to go there. But all of these are metals that are available on the commercial market in thin foils, and you can use any of them. So, well, why would you want to use any specific material other than copper, which is what we primarily use? There are applications where you may want to have unique thermal coefficients of expansion on sensors, and a particular metal material may meet that need for you. There are some metals that may be more affine to some chemical species that you want to sense, and they're available to you. We are doing some investigations with magnetic materials, some interesting things there that you'll see. In manufacturing, this is a click and cut device showing a layout of an array of SansEC sensors that actually Trong Nguyen came up with this concept when we started the project. A click and cut is a device that crackers use to make cards and all kinds of really cool things. And Trong had this idea with some, just every now and then we get just like a small amount of money and to just say, do anything you want with it. Trump bought one of these things and started making SansEC sensors with them. We're like, wow. We talked to the person that distributes this product, I think in North Dakota, and she's like, NASA? what do you guys do with our equipment? And we told her, she's like, wow, that's really cool. Can you use that in a write-up? I said, sure. But it's been a very useful tool. It's not the only way to make SansEC sensors. It's good for rapid prototyping in a lab where you want to test concepts very quickly. You may decide to make your SansEC sensors in many different ways. The designs are not limited to the square sensors that you see. They can be any shape. You see some regular shapes here, triangular, square, hexagons, and circles. But they can be any shape. You'll see some of these on the tour, later tour. We go from a single dimension to 2 dimensions. You can make arrays of these sensors to cover a tile surface that you might be interested in. You go into the 3rd dimension. You can stack the sensors and use them for applications where you may need to go into the 3rd dimension. There is a cube made of SansEC sensors. It could be a container. You put something in the container and you sense the thing, or you could be, we're not even sure how to apply this. It just works. That's the other thing with SansEC. I'm a skeptic. Every time George comes up with really great ideas, and our team comes up with great ideas, and I always go, and we'll say, that's going to be kind of hard, and we'll brainstorm it, work it out, and it just works. And then we figure out why. Sometimes we do it before that, and I'll talk about that in a little bit. Talked about, Keith mentioned size. What is the length scale of operation of a sensor? Can you make a SansEC sensor the size of a galaxy? Okay, well, that might be too large. But Dr. Wong, in one of our computational exercises, we were going to make a 30 millimeter, I think, sensor, and we accidentally input the wrong components, and we ran it, got the solution back, and said, that looks pretty good. Everything. We said, wait a minute, it's 300 meters on its size. So you can make very large SansEC sensors. That may be good for things where you want to do ground penetration. You want some big surface area where you put a SansEC sensor on the ground and want to do ground penetration to look into the surface. I know that there's a member in the audience today that has, I think he will talk about a device that he has for ideas like that. But going the other way, going smaller, Dr. Golden talked about nanotechnology, moving smaller, down the length scale, millimeter, microscale, nanoscale. I have a student, a high school student, brilliant kid. He has a concept, I won't divulge his concept, but it's going to require making SansEC sensors out of nanotubes. And I've got some friends out at Langley in the chemistry group that have worked some nanomaterial projects in the past. We're going to go over and talk to them and say, how would you do this? And we're going to relay that information to you later. How do you go down? How do you go down in scale? That may have some interesting applications in the biomedical field, either surface contact with the sensors on the skin, or maybe things that are ingested. I'm going to speed up a little bit because I think I'm running a little long. Computational models. We use computational models to actually inform our investigations. Dr. Woodard was a tried and true believer of the Edison method, which is very good, it works. Try, fail, try, succeed. Okay, you learn something. You might learn quite a bit there, but you can do the same thing computationally. And Laura Smith is our computational expert. Dr. Wong is another of our computational experts. And we were able to convince the project a couple of years ago, let us apply computational electromagnetics to some of our problems. So it's going to be a long learning curve to get it up to speed. But when we get there, it's going to rapidly take off. And it did just that. Within a year, we were running models that on things where we didn't have to cut materials. We didn't have to use money to make things. We could test concepts out quickly in the computer. And we use a tool called FICO that we can get a force multiplier by using these computational tools to inform our experiments. And then our experiments feed back into the models of what we learned. And then we do that iteration again. And it's a very powerful way of doing that. Here's a couple of computational visualizations for some damage on composite materials. Visualization here shows no damage. The top visualization shows I believe it's a 2 mil, not 2 millimeter, a 2 mil delamination between the ply layers of a composite panel substrate. And you get the dramatic electric field change on that, which shows up as a frequency change and a resonance change. A puncture is obvious. We can see where the electric fields are going through, and then a void within the material. So these computational tools are very powerful. We do parametric experiments, both physically and computationally, where we lay out a geometric series and get resonant responses like you see there. We vary the geometric shape, we vary the size, we vary the trace, we vary the gap. We've done a lot of these things that you're going to be the benefit of all of this research to kickstart you for the things that you want to do. We've got a database of knowledge on here. Here's a series where we were doing the varying the gap within SansEC to get parametric information on how does the SansEC physically change, and then we'll put actual theory to and equations to why this happens this way. Here's one where we're varying the trace widths of the SansEC sensors. And you see in our computation, I believe the red line is our computation. This was a model that Laura Smith ran. And you see the red line is our computation, and the blue line is our measurements. And we're like, why is it? It's not exactly the same. But hey, that's pretty good. It's close enough. We did that a couple of years ago or so, and then it wasn't until a year later we were looking back at this and we were like, that difference was nagging at us. We're like, why is that difference there? Turns out that that's actually a measurement. The sensors here are embedded in a laminate material. The sensors that we modeled are modeled in free space. There's no laminate around the material. That difference is the dielectric property of the laminate. Incredible. It's absolutely incredible. And we found that out later. We're constantly reviewing our work and trying to make it better. Here's some more parametric models showing electric field distributions on the SansEC sensors. Here's a parametric experiment using the new metal, where we're using it to attempt to penetrate into carbon conductive, more conductive materials. SansEC, if you place them on a conductive surface, they short out. So they don't work on conductive materials. They work on dielectric materials. We had a challenge from our program, which George is going to talk more about our program, which is aviation safety. That we need, can you guys get these sensors to work on carbon composite structures that have a little bit more conductivity? They're not totally metallic, but they're not dielectric either. And Traton Wang and the rest of the team, we put our heads together and came up with this concept of using a magnetic new metal to enhance the magnetic fields to essentially do an impedance match between the sensor and the sensing structure that we were doing. And like I said, I was pretty skeptical. That was a really hard challenge. And like I said, I was very skeptical that we would be successful at it. I worked at it for about 6 months, and we succeeded. It was amazing. There's 2 interrogation methods that we talked about. One uses the network analyzer. The other uses a spectrum analyzer base. And there's some technical differences with it, but we'll talk about those later. But essentially, on this network analyzer, it's a vector instrument, and you get your resonance spike goes down. On the spectrum analyzer, it's up. But there's more to it than that. But those are 2 different instrument methods that can be used. We can use a reflection technique where we use one antenna, we ping the sensor, and it responds back. Or we can use a bistatic approach where we use two antennas with the receiver in a transmit mode, where we transmit on one antenna and receive at the other antenna. That can increase your dynamic range and your measurement sensitivities. I talked about going to far field, configuration at the top with the network analyzer connected to the loop antenna and the SansEC in the vicinity of the loop antenna. Our goal was a 1 meter standoff. Turned out we could do that across the lab. 30 feet was easy, actually. We're also using a signal source. You can drive the antenna, and then just use a handheld spectrum analyzer instead of the network analyzer. You don't eliminate this cable in that way. And again, you can achieve a really good standoff distance. We're initiating a new thought with SansEC of breaking it into a hardware component and a software component. The hardware is the SansEC itself, the sensor, whatever you make it out of, and the shape and the geometry. But the other part of it is the signals. Grabbing the signals and analyzing the signatures. Here we have a magnitude response as a function of frequency, another magnitude response where we get a shift, and you see some bandwidth increase that you can use as intelligence, looking at it in a phase response and an uncalibrated phase. These are signatures that you can apply to gain intelligence about the material that you're sensing. So instead of just using the resonance response and a frequency shift, you may combine that with what's phase response and gain extra intelligence of the material under test. And so we need to bring together people that are skilled in digital signal processing to use techniques from information theory, statistical analysis, and digital signal processing and other algorithms to look at signals in a way that you can infer greater intelligence. That is the software side. If you think of the computer revolution, you have this hardware box, and then you have this software development. And it was the guys that did the software development that really took off. There's infinite ways that you can manipulate the software. So we're just starting to think about that approach. So we'd like you to start thinking about it as well. There's one concern and issue is in the United States and also across the world, you can't just radiate at any frequency. So your design may have to take into account the frequency spectrum, the legal aspects of the frequency spectrum. And there are certain bands, ISM bands, I forgot exactly what that stands for. Anybody? Jay?
Industrial, scientific, medical.
Industrial and scientific and medical bands. There are bands that are set aside specifically for frequencies of operations for those particular type of applications. And there's some others as well. So you can find space to operate the sensor in the open world. And the fact that we can also use low power may actually help. Okay, we live in a universe of length, time, mass, and charge. And SansEC can measure all of those. You look at fundamental equations in physics, we have things like kilograms, meters per second squared. We can measure the kilograms, we can measure the meters, and we can measure maybe the time. We'll see an interesting experiment in the lab. So SansEC sensors are a new dimension of sensing. They can sense a multiple of parameters in every field that we can think of. And Dr. Woodard left off with a concept using SansEC sensors on what was a proposed Mars flyer, an aircraft that we were going to fly on Mars, and tile the surface of the aircraft to measure various flight conditions. And George Sikorsky, when he met with SAN, said, I've got a real-world application for you. We want you to work with us. George recruited Dr. Woodard and Trauton to be part of our team. We started an application area into aviation safety, where the concept was to tile the surface of our new composite aircraft that are emerging every day for lightning strike protection, where we place this SansEC sensors as the smart skin of the aircraft in a way that we achieve lightning strike protection, damage detection, and enhanced shielding effectiveness from external signals that we don't want in the aircraft. Currently, the way that we shield composite aircraft is a metal mesh. It's a good method. It works. It protects the aircraft against lightning. We'll see some of that in the lab today. But by enhancing that, by making it into the simple spiral, we can add these added functions. And I just mentioned the three that we were chartered with. It goes beyond that. If icing builds up on the outside of your aircraft, SansEC sensor looks in just as well as it looks out, detect icing. Other phenomena features aerodynamic loads. We've done a number of experimental investigations and applications. And with that, I'm going to turn it over to my boss, George Shukowski, who's a brilliant leader in this SansEC area. There are amazing things that I cannot even describe to you. The concepts and things that he comes up with that specifically for aviation safety. Thank you very much for your attention.